Okay, welcome back, friends. In the last session, we have seen this Poisson's equation. What is this Poisson's equation? Poisson's equation relates the potential with the charge. Clear? Yes? I'm good now. Thank you. And here is the thing. I have given some this problem here and I have given procedure as well. So how many of you are done with this one? Good. Some of your friends had answered very good. Very good. The procedure and everything is in front of you. Good. Let us do this one. First, you need to find out the volume charge. Potential is given. Then you can find out the total charge. Fine. Let me turn the page here. How do you find out the volume charge? Rho V is equal to minus epsilon naught into del square into V. What is this del square into V? 1 divided by r square sin theta dou by dou r into r square sin theta into dou V by dou r plus dou by dou theta into dou by dou theta into r sin theta by r into dou V by dou theta plus dou by dou phi into r divided by r sin theta dou V by dou phi. Here the potential, let me go back. The potential is only the function of, here the potential is only function of r and r. Here the potential is only function of r. So there won't be any differentiation with respect to theta and phi. So what happens to this one? Here it is. Del square V is equal to 1 by r square sin theta dou by dou r square sin theta dou by dou r into V. What is V? Minus 6th r to the power of 5 by epsilon naught. So here it is. Del square V is equal to 1 by r square sin theta dou by dou r square into sin theta. What is the differentiation of this one? Minus 30 into r to the power of 4 divided by epsilon naught. Just bring the constant outside. Minus 30 into sin theta divided by r square sin theta epsilon naught dou by dou r to the power of 6. Is that correct? So further differentiate that one. I'm going to turn the page here. Okay, beta. So here it is. Del square V is equal to minus 30 by R square 6 into R to the power of 5 divided by epsilon naught. So del square V is equal to minus 180 into R to the power 3 by epsilon naught. So here rho V is equal to minus epsilon naught into del square into V minus epsilon naught into minus 180 into R cube by epsilon naught. So the rho V is equal to 180 into R to the power of 3 units are coulomb per meter cube. So you have got a volume charge beta. Then how can you find out the total charge? Perform the volume integral. So how do you get the total charge? Volume integral of rho V into dV. Clear beta? What is this dV differential volume? R square sine theta dr d theta d phi. And what about the limits beta? R limits. R is less than or equal to 1. It is a sphere. So it is from 0 to 1 beta. So R is from 0 to 1. For the sphere, anyhow, theta is from 0 to phi. Phi is from 0 to 2 pi. So here it is 180 into R cube into R square sine theta dr d theta d phi. One 180 R to the power of 5 sine theta dr d theta d phi beta. Okay. Separate out the limits here. 180 into R to the power of 5 into dr. Here it is sine theta d theta. Here it is d phi. 180 into R to the power of 6 by 6. The limits are from 0 to 1. Here minus cos theta 0 to pi. Here it is 5 0 to 2 pi. Upper limit minus lower limit. Here it is 30. One 120 pi coulombs is the answer better. We'll take one more question. I'll going to turn the page here. One 120 pi coulombs, option C. Some of your friends have already answered it. Very good. Let us take one more question. In source free region, if the electrostatic potential phi is equal to 2x square plus 2y square plus Cz square. The value of constant C must be. Just a minute, I'll change this marker. You try this. Yes, what is answer for this? In a source-free region, here it is. Source-free. So in the source-free region means what? Charge is 0. Yes. Consider the Laplacian of this Poisson's equation. Here it is. Yes. Del square V is equal to minus rho V by epsilon. It is said that it is a charge-free region. So what happens to this one? Here it is. Del square V is equal to 0 beta. Yes. So here it is. Dou square by dou x square of V plus dou square by dou y square of V plus dou square by dou z square of V is equal to 0. So what is the double differentiation of this one? Is with respect to x 2 into 2 into 1 plus 2 into 2 into 1 plus 2 into 1 into c, which is equal to 0. So here it is 8 plus 2c is equal to 0. C is equal to minus 4 is the answer. Yes, minus 4 is the answer. A simple, straightforward question. Clear? Let us have one more question. I'll go to turn the page. This was one of your previous year's question. The three values of a one-dimensional potential function phi shown in the given figure and satisfying Laplace equation are related as phi 2 is equal to 2 phi 3 plus phi 1 divided by 3. Phi 2 is equal to 2 phi 1 minus phi 3 divided by 3. Phi 2 is equal to 2 phi 1 plus phi 3 by 3. Phi 2 is equal to yes. Three values of one-dimensional potential function phi. Here the potential is represented. V is represented with the phi shown in the given figure and satisfying the Laplace equation are related as. It is said that they are satisfying the Laplacian equation. Let me turn the page here. What is the Laplacian equation? Del square V is equal to 0 is the Laplacian equation. Let me go back. Three values of one-dimensional potential function. Here it is one-dimensional. Clear? Yes. Let me consider this as some coordinate system x-axis. Here it is 0, 0, 0. Yes. So it is a one-dimensional. Potential is dependent only on the x. When the x is equal to 0, the potential is phi 1. When x is equal to d, the potential is phi 2. When x is equal to 3d, the potential is phi 3. Yes. So the potential is a one-dimensional function. Here it is. Let me expand this one. Here it can be written as dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square is equal to 0. These two parts are 0. Potential is dependent only on the one coordinate. It is a one-dimensional potential function. Clear? So here it is. This will become dou square v by dou x square is equal to 0. I want to get the expression for v beta. Yes. So what I'll do, I'll integrate on both sides. If I do one-time integration, what you're going to get? Dou v by dou x is equal to 0. If I do one more time integration, sorry, one-time integration will lead to some constant C1 here. Some arbitrary constant C1. Even you can cross-check one more time. Differentiation, right? If you differentiate this one, you will going to get this. One more time integration, what happens? V is equal to C1 into X plus C2. Clear? Yes. Apply the boundary condition beta. Yet phi is equal to, yet x is equal to 0. What is the potential? It is phi 1. Clear? Yet x is equal to 0. The potential is equal to phi 1. Just substitute that value here. Phi 1 is equal to C1 into 0 plus C2. So here C2 is equal to phi 1. At x is equal to d beta. What is the potential? Potential is equal to phi 2. So here it is. Phi 2 is equal to C1 into d plus C2 value is already phi 1. So from here C1 is equal to phi 2 minus phi 1 by d. Here it is C2. Here it is C1. Let me turn the page here. So what is the complete expression for the V? V is equal to C1 into D. What is the C1 beta? Phi 2 minus phi 1 divided by D. C1 into X plus C2. What is C2 is phi 1. There is one more boundary condition. What it is? When X is equal to 3D, the potential is phi 3. Yes. So at X is equal to potential is phi 3. Substitute that point. Phi 2 minus phi 1 divided by D into 3D plus phi 1. So phi 3 is equal to 3 phi 2 minus 3 phi 1 plus phi 1. So here phi 3 is equal to 3 phi 2 minus 2 phi 1. We want expression for phi 2. Phi 3 plus 2 phi 1 divided by 3. This is what required. Phi 2 expression is required. Let me go back. What is the phi 2? Phi 3 plus 2 phi 1 by phi 3. Phi 3 plus 2 phi 1. Phi 3 plus 2 phi 1 by 3. So option B is the answer. Phi 3 plus 2 phi 1 by 3. Option B is the answer. So these are the some of the varieties of questions on the Poisson's equation. Clear? Yes. Now let us proceed further. There is a one more technique in the electrostatics which you need to remember. That is the method of images. So what are the things we have done? We have discussed what is called a gradient relation, and after that a Poisson's equation. We have discussed what is called a potential. Yes, potential difference, gradient relation, Poisson's equation. There is one more thing, one more concept here in the electrostatics. Method of images. Method of images. What does that mean? Let us consider the infinite sheet. Let us consider the infinite sheet. This is the infinite sheet. If I draw a line and if I put a dots, what does that indicate? It indicates the infinite sheet. Now I'm going to place some charge here. I'm going to place some charge Q. It is extending from minus infinite to plus infinite, and it is grounded. And it is grounded. Okay. So what I'm doing here, it is an infinite extent and it is grounded. So what happens here is the charges which are the electric field which is coming from the, yes, boundary conditions we'll discuss. Capacitor problems also we'll discuss later. I'll take the boundary conditions of electrostatics and magnetostatics combinedly, inductor problems and capacitor problems combinedly, so that you can easily observe them, easily you can analyze them, you can easily remember them, instead of taking them separately. So I'll take the inductance and the capacitance of the coaxial cable at a time. Okay, instead of discussing them separately. And boundary condition problems, instead of taking them separately, I'll take it as in a single slot. Okay, that I will going to do in the magnetostatics. Anyhow, concentrate here. A method of images. What is this method of images here? There is an infinite sheet on which we are placing the charge. Infinite sheet, it is the infinite extent and it is grounded here. Observe carefully. So what happens? The electric field which are coming from the charge will going to be directed towards the sheet like this. So the electric field which is coming from the charge will going to point towards this one, and it will going to induce the negative charge. And it will going to induce the negative charge on the sheet. Yes. And how it will going to point, electric field will be normal to the sheet, isn't it? Normal. The electric field which is coming from this one will not going to dance like that. The electric field will be normal. Isn't it? That I have already explained. How the electric field can exist on the conductor normally. It cannot exist tangentially. That I have already explained in the last session. Okay. So how much all the electric field lines which are coming from the charge will going to direct towards the sheet. So it will going to induce the charge on the sheet. How much charge it will going to induce? The same charge whatever you have placed here. Because it is the infinite extent. All the fields will be directed towards this one, isn't it? Yes. So how the scenario is, let me draw this one carefully like this. There is an infinite sheet. I am placing the charge here. All the electric field lines will be directed like this, So it will going to induce a charge on this one. What is this one? Here it is minus Q. That is the story. Hope you can visualize now. So the induced charge on the sheet will be equal to the same charge what you have placed. Remember, that happens only when it is of infinite extent. Let us say if it is a finite extent. Let us say if it is a finite extent. If it is a finite extent, what happens? Only, let us say it is creating some lines. Only some lines will be directed towards this one. Remaining lines will go into direct in other way. So the induced charge will not be equal to the charge which is placed. The induced charge will be equal to the charge which is placed only when it is of infinite extent. So all the electric field lines which are coming from the charge will go into direct towards that one. That is the one observation. The other observation is it must be grounded. What is the property of the ground? It will contribute for the deficiency and the excess of charges. If there are excess of charges, it will going to take. If there is any deficiency of the charges, it will going to give. That is the property of the ground. So if the charges, whatever the charge you are placed, if that many charges are needed, it will going to take from the ground. Yes, fine. Now here the question is, I want to find out the electric field. The scenario is like this. There is an infinite sheet, there is a charge. And there is an electric field here. I want to find out the electric field somewhere here. So the electric field here is due to this charge. It due to this charge, this charge, this charge, this charge, this charge, and so on. So it is a theoretically okay. Practically, you need to add up the charges. Let me show you here. You need to add up the charges right from in the 2 dimensions in the infinite plane. Isn't it? I want to find out the electric field here. Can you find out the electric field here? I want to find out the electric force here. Can I find out? I want to find out the potential here. Can I find it? Can you find out the electric field here? Somewhere here? Yes. Is due to this charge. Is due to this charge, this charge, this charge, this charge, this charge, so on. So theoretically, it is a very tedious thing. It is a very lengthy thing. That is the reason why what we're going to do, we're going to develop some equivalent theory for this one. Clear? What is that equivalent theory? There is a charge here. So what we're going to do, I'm going to place some imaginary charge beneath the sheet, below the sheet. How the electric field lines will be like this. It is an image charge. Is there any such charge? No. Just for the analysis purpose, to make the analysis simple, I'll going to place what is called an image charge. It is a very simple technique. If there is an infinite sheet is there and if there is a charge, you want to find out the electric field, force, potential, whatever it may be. So if you go by that regular approach, it is a very complicated thing. What I'll do, I'll going to place some image charge for the analysis purpose and remove the sheet, throw it away. Now, can you find out the electric field here, beta? Can you find out the force here? Can you find out the potential here? Yes, easily. So what is the electric field here is due to discharge and discharge. Now it is a two charge system. And observe here, the nature of the electric field, the nature of the electric field here and the nature of the electric field here are same. Yes or not? The nature of the electric field here and here are same. When the nature of the electric field here and here are same, here and here are same. So for my analysis, this would be more appropriate because it is just a two charge system. Clear? Yes. Now let me turn the page here. We're going to solve one problem that will clarify all our questions. It is a very simple thing here. Okay. Let me show you with some example. Now let us take one example here. There is an infinite sheet here. Which is extending from minus infinite to plus infinite. There is a charge here. Point charge here. There is a line charge here, let us say. Minus rho L, let us say. And there is a volume charge here, rho V here. Coulomb here. Coulomb per meter here. Coulomb per meter cube here. And there is an infinite grounded sheet here. How this can be represented? So this can be represented like this. Here there is a charge here. Remove that sheet and throw it away. If there is a charge here, there is a negative charge here. Rho V coulomb per meter cube. Here it is rho L coulomb per meter. So remove that sheet and throw it away. Charge. What is the image charge for this one? Is minus Q. Image charge for this one is plus rho L coulomb per meter. Here it is coulomb. What is the image charge for this? Minus rho V per coulomb. Rho V for minus rho V coulomb per meter cube. All these are image charges. What these are? Clear, beta? Let us take one question here. It will clarify all your doubts. This was asked. Once only there was a question on this concept. Only one question was asked in the GATE paper. Before going into that, let us take one question from your EC paper. From the EC paper. After that, we'll take that question from the electrical paper. Very simple concept it is. Yes, I'm going to turn the page here. Let me write down the question. The force on a point charge plus Q kept at a distance D from the surface of an infinite grounded metal plate is option A 0, Option B, Q square by 16 pi epsilon d square away from the plate. Option C, Q square by 16 pi epsilon d square towards the plate. Option D, Q square by 16 pi epsilon d square towards the plate. Yes, let me turn the page here. One of your friend is asking why electric field is perpendicular. Yes, electric field can exist only perpendicular to the conductor that I have already given while explaining the applications. Examples on the Gauss law. You can go back and check out. Clear? Yes. Yes, how do you do? This is a very simple thing, beta. Let me turn the page here. Let me go back. The force on the point charge Q kept at a distance d from the surface of an infinite grounded metal plate is. There is an infinite grounded metal plate. It is an infinite and it is grounded. And there is a charge Q. The distance from here to here is d. Okay. Now, how this can be represented equivalently? Here it is charge Q. So if it is an infinitely grounded sheet is there, just to remove that one, throw it away, and you can just place some image charge Q. So here the distance is d. Here will be for the mirror also distance d. So what is the distance? For overall distance here it is? Overall distance is d. How the force will be acting? Force will be acting from positive to negative. That means this is a force direction beta. That means towards the plate, isn't it? So what is the force here? Just I'll take the magnitude here. Force magnitude is equal to Q into minus Q divided by 4 pi epsilon into 2d square. Here it is. Magnitude of the force is equal to Q square divided by 16 pi epsilon d square. It is towards the plate, that too. Let me go back here. Towards the plate. Option C is the answer. 16 by Q square by 16 pi epsilon d square towards the plate. Very simple beta. If the charge is there, infinite sheet is there. If it is asked for force or electric field, whatever it may be, remove the sheet, place the image charge. Now it is a two charge system. That's all it is. Okay, fine. So this is for the it is for the infinite sheet. If the semi-infinite sheets are given, then how you need to proceed? Let us take some special cases of this. I'm going to turn the page here. Let me explain with the help of some examples. Example number 1. If some semi-infinite sheets are given for you, that means two semi-infinite plates are inclined at certain angle. Yes, very good. Yes, this is image charge will be there only for the grounded sheets, isn't it? So now let us take this example better. Come on, observe here. There are two infinite sheets beta like this. Semi-infinite sheets. Here it is grounded. Okay, they are inclined at certain angle. Here is a charge Q. Okay, so how many image charges will be there for this one? There are two semi-infinite sheets here. Then what would be the constellation of the image charges? If the semi-infinite sheets are given, you need to take one sheet at a time. What you need to do? You need to treat one sheet at a time. You have to treat this as an infinite sheet. And what is the image for this one with respect to this? Somewhere here minus Q. Clear? Yes. So you need to treat one sheet at a time. This is an infinite sheet. This is an infinite sheet. With respect to this one, image is somewhere here, minus Q. With respect to this one, the image is minus Q. With respect to this one, the image is minus Q. With respect to this one, the image is, sorry, this is plus Q. Minus Q is already there. You should not add one more minus. If you add one more minus Q, it will continue without any end. I'll repeat again what we are doing here. You need to take one sheet at a time. Okay. So here with respect to this, the image is minus Q. With respect to this, the image is minus Q. With respect to this, the image is plus Q. Here it is minus Q. Clear beta? Yes. So how many image charges you will going to get? Total 3. Now can you give me any formula for me? So with respect to this one, you have to extend this as an infinite sheet. So with respect to this one, the image is minus Q. With respect to this one, the image is minus Q. With respect to this, the image is plus Q. With respect to that, the image is minus Q. Now, can you suggest me any formula beta? I'll write the formula like this. 360 divided by 90 minus 1. So 3 is the image number of image charges. Clear? Let us proceed further. Example number 2. Now let us take the angle of inclination as 60 degrees beta. So how many image charges you will going to get? 360 divided by 60 minus 1. How many image charges? 5 image charges. Let us check. Is that correct? Infinite sheet is like this. Here it is 90 degrees. Here it is 45. Somewhere around here it is 60. Yes. So you need to extend one sheet at a time. My charge is somewhere here, Q charge. So the charge here is Q. Image charge for this one is Q. The constellation looks like this. Like a hexagonal. Yes. So actual charge is this one. And the remaining are 1, 2, 3, 4, 5. 5 are image charges. Clear? Yes. Fine. Observe here, beta. One sheet at a time. With respect to this one, what is the image? This one, somewhere here. Right? So here it is. Minus Q. With respect to this one, what is the image? Somewhere here. Minus Q. With respect to this one, what is the image? Somewhere here, beta. Plus Q. With respect to this one, what is the image? Somewhere here, beta. With respect to this one, what is the image, beta? Somewhere here. Plus Q. So if you draw this one, actually, it will going to look like a hexagonal. Clear? Yes, fine. So let us take one more example, beta. I'm going to turn the page here. Example number 3. (360 divided by 120 minus 1). How many image charges? 2 image charges. Is that correct? Let us check. 360 divided by 120. 3 minus 1, it is 2. So 2 image charges. Is that correct? Clear, beta? 90 degrees is somewhere here. So 120 degrees is somewhere here. Yes. Here it is grounded, beta. So here it is 120 degrees. Here is a charge Q. Here it is extend this one as a and treat this as an infinite sheet. Suppose if you observe with respect to this one, what is the image beta? Somewhere here minus q. Yes. With respect to this one, what is the image beta? Somewhere here minus plus q. With respect to this one, what is the image beta? Somewhere here minus q. Yes or not? With respect to this one, what is the image? Plus q. With respect to this one, what is the image? Minus q. With respect to this one, what is the image? Plus q. Does it stop here? No. Without any end. This one, 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 this one. You'll get the infinite image charges. Are what is this one? So this formula is not valid. Then what is the limitation of the method of images? See, what is this one? Here it is image of the image charge. What is this one? It is the image of the image charge. What is this? Is the image of this one, and this is the image of this one, and this is the image of this one. So the image charge should be beneath the sheet. That means other side of the sheet. See here, whatever the image charges you are placing other side of the sheet. Now there is no image charge here in the region of interest, where you want to find out actually the electric field or electric force and so on. So whatever the image charges is there, they must be here. So the no image charge should be here. Image charge means just for the analysis, these are the fictitious charges. Fictitious means something imaginary. They do not exist. Just you are placing them only for the purpose of analysis. So whatever you do, you have to do other side of the sheet, but not in the region of interest. But see here, whatever the image charges is there must be here, but not in the region of interest. So unfortunately, what you are getting the image charge in the region of interest. So if the image charge is there in the region of interest, then method of images technique can't be applied. Yes. So what is this one? Here it is. Just I'll call it as a image of the image charge. Image of so on. So what is observation beta here? If the image of image charge exists in a region of interest, then method of image technique can't be used. Clear beta? So that is the limitation. Let me turn the page here. Example number 4. (360 divided by 0 minus 1) tends to infinite. Is that correct? Yes, let us check. That means two sheets are parallelly placed. Here it is grounded. Here is a charge I have placed. So with respect to this one, what is the image? Minus q. With respect to this one, what is the image beta? Here, minus q. Does it stop here? No. Why? With respect to this one, what is the image of this one? Plus q. So somewhere here. With respect to this one, what is the image of this one? Plus q here. Does it stop here? No beta. With respect to this one, what is the image of this one? Minus q. And so on. It will continue. In an engineering service paper, there was once question on this formula based question. If the angle of inclination is 30 degrees, how many image charges will be there? 11 image charges will be there. That was one of your previous question in the engineering service paper. I'm going to turn the page here. So, note. Number of image charges. What are the number of image charges? 360 divided by 5 minus 1. What is this 5? 5 is a angle of inclination. Angle of inclination between two semi-infinite sheets. For example, this was one of your ES question, engineering service paper. So angle of inclination is equal to 30 degrees. Number of image charges is equal to C60 divided by 30 minus 1. There was 11 image charges. Okay, we'll take one question here. I'm going to turn the page. Let us have a question. Two semi-infinite conducting sheets are placed at right angle to each other as shown in figure. A point charge of Q is placed at a distance of D from both sheets. The net force on the charge is Q square by 4 pi epsilon naught K vectors by D square, where K is given by this is an infinite sheet. Here it is grounded. Here it is X, here it is Y. Here it is D. Here also it is D. Here is a charge Q. Option A is 0. Option B is minus 1 by 4 X cap minus 1 by 4 Y cap. Option C minus 1 by 8 X cap minus 1 by 8 Y cap. Option D 1 by 2 root 2. 1 minus 2 root 2 by 8 root 2 X cap plus 1 minus 2 root 2 divided by 8 root 2 Y cap. Yes, this was asked for 2 marks beta. He is asking what is the force on this one. Yes, how many image charges it will going to have? It will going to have a 3 image charges, isn't it? So the force also he has given. He is asking for the K vector. So this can be written as, you have to treat this as an infinite sheet. So with respect to this one, minus Q. With respect to this one, minus Q. With respect to this one, plus Q, and so on. So just to remove that sheet by placing the image charges beta and find out the total force. It is a regular electrostatic problem. Now do that one and compare that one and find out the K vector. I'm going to turn the page here. Here it is X, here it is Y. Here is a charge Q beta. With respect to this one, here it is the image charge is minus Q. with respect to this one minus q, with respect to this one plus q, and there is a minus q. That's all it is. So, and the spacing is also given. Here to here distance is d, here to here it is d. So what happens to this point? This point is d comma d. This one beta, d comma minus d. This one beta, minus d comma minus d. This one, minus d comma y, minus d comma d. Let me give the numbering. I will going to call it as the first charge, number 1. Here it is number 2. Here it is number 3. Here it is number 4. So I want to find out the question is to find out the force on that one. So what is the force on that? F total is equal to force on first one due to second one. Force on first one due to third one. Force on first one due to fourth one. Clear beta? How do you find out the force? F is equal to Q1 into Q2 divided by 4 pi epsilon r square into r cap, where this unit vector is vector by its magnitude. So here it is Q1 into Q2 by 4 pi epsilon vector by its magnitude cube. Clear? I'll going to turn the page here. The rest of the thing is algebra. You can also do, isn't it? I'll going to turn the page here. Yes. Please help me. If I go wrong anything, if I do anything, any mistake, please help me. What is the force on first one due to the second one beta? Q into minus Q, it is minus Q square divided by 4 pi epsilon. D minus of minus D beta, here it is 2D. 2D by its magnitude is 2D. 2D x cap beta. Magnitude is 2D cube. Plus force on first one due to the third one beta. Q into Q beta. It is Q square. Divided by 4 pi epsilon. D minus of minus D, it is 2D. X cap plus 2D y cap divided by square root of 4D square plus 4D square whole cube plus Q into Q, it is minus Q square by 4 pi epsilon. D minus of D, D minus D is 0. D minus of minus D is 2D y cap divided by its magnitude cube. Come on, simplify this one. Q square by 4 pi epsilon is, you can take it common. Q square by 4 pi epsilon, you can take common. Now rest of the thing is algebra. You can do that one, but do it nicely with patience. So here it is minus x cap by 4D square minus y cap by this term 4D square plus 2D x cap plus 2D y cap divided by, here it is 2 root 2 into d whole cube. Yes, beta. So further, how this can be written? Q square by 4 pi epsilon minus x cap by 4d square minus y cap by 4d square. Here it is 2d x cap plus 2d y cap divided by, here it is 8 2 root 2 into d cube. 8 into, yes. So further, q square by 4 pi epsilon x cap by 4d square minus y cap by 4d square. Here it is x cap plus y cap divided by 8 root 2 d square. So here it is q square by 4 pi epsilon d square x cap 1 by 8 root 2 minus 1 by 4 plus y into 1 by 8 root 2 minus 1 by 4. Bus. So it is matching with the option q square by 4 pi epsilon d square x cap into 2, it is 8 root 2 LCM. It is 1 minus 2 root 2 divided by 8 root 2 plus y cap into 1 minus 2 root 2 divided by 8 root 2. If you compare this one with the given question, k vector comparison, here it is q square by 4 pi epsilon naught d square into k vector. So by comparison, here is a k vector. Yes. So what is the answer, beta? Option D is the answer. Okay, let us take one more concept, beta. One more miscellaneous concept, that is Ohm's law, current and current density. Let me turn the page. I'm going to turn the page here. Current density, and then Ohm's law. Before going into the magnetostatics, what are the things we have discussed here? Only two things need to be discussed. One is the boundary conditions, other one is the capacitor problems. But I'll not going to take them separately, beta. As I said earlier, I'm going to combine the magnetostatics and electrostatics boundary conditions. I'm going to discuss in a single lecture, and I'm going to discuss the capacitor and inductor problems in a single lecture. Fine. So before going into the magnetostatics, let me put some base here. Let me put some foundation here, which is with the help of what is called a current density, and then Ohm's law. Fine. Current is represented with the I amperes. Current density, it is represented with the J. Units are ampere per meter square. And then we're going to discuss what is called Ohm's law. Let us consider the conductor, a perfect conductor. How do you get the perfect conductor? I mean, conductor means something like a silver or a copper or aluminum, isn't it? Let us consider the perfect conductor or a good conductor, whatever it may be, something like a silver or a copper or aluminum. There is a conductor here. This is subjected to the external electric field. What these are? These are external electric field. Is represented with the E. Units are volt per meter. How do you get the external electric field? From the battery. Okay. And conductor is very rich of free electrons. Let me show you like this. Positive here. One free electron, something like a aluminum. One free electron. What is that? This is a nucleus and this is a free electron. Dot is a free electron. So this is a nucleus and dot is a free electron at the room temperature. When I subject the conductor to the external electric field, what happens? This electric field will going to exert the force on the charges, on the electrons, and electrons are being attracted. So what is the force expression is given by? F is equal to Q into E. What is this Q? Number of electrons into charge of electron. That is a Q. Okay. So what happens here? Electrons will start moving like this. So when the electrons start moving, what happens? There is a current flow. dq by dt. Units are coulomb per second. So generally it is amperes. So the current flow happens opposite to the direction of electron flow. I ampere. You know all this mechanism beta. Clear? Yes. You would have learned your circuit theory starts with this one. But I want to define something new. This current is spread over the conductor. Now we're going to define what is called a current density. Current crossing through the unit area. Observe here carefully. So the I current is distributed over the cylinder beta. Now let us consider a small piece of area here. Here it is dA. And what is the current crossing through this one? Here it is n cap, here it is J. Units are ampere per meter square. Clear? So how do you guys going to define the new current? I is equal to, sorry, J is equal to, I'm going to define the new current. J is equal to di by dA. Units are ampere per meter. Current crossing through unit area. So the di is equal to J dot dA. So the I is equal to surface integral of J dot dA. Here it is ampere per meter square multiplied with the meter square. Here it is ampere. Clear, beta? Yes. So what it is a new current? Current crossing through unit area. That's all it is. There's nothing much to discuss about that. Yes. So the current density direction is also in the direction of the current flow. Here it is J, units are ampere per meter square, beta. Clear? I'm going to turn the page here. Now I'm going to define what is called Ohm's law. What is the Ohm's law? J is proportional to E. Displacement current is proportional to the E. If I apply more electric field, more electrons are being attracted, more current flow happens, more current density. Isn't it? If I increase the external electric field at a constant room temperature, that is the thing. So if I keep on increase the electric field, more electrons are being attracted, more current flow happens, more current density. Yes, beta? So here J is equal to sigma into E. This is called Ohm's law in the field form. Ohm's law in the field form. Yes. What is this sigma? Sigma is mho per meter. Conductivity. Remember, but what you are learnt in your high school physics, sorry, not. What you are learnt in your circuit theory is something different. What it is? V is equal to IR. How you have got from here itself? In circuit theory, we will do some approximation. In what are the approximations in the circuit theory? E is equal to V by L. Conductivity is equal to 1 by rho. J is equal to I by A. These are the approximations are done in the circuit theory. Okay. Then what you will going to get? J is equal to sigma into E. In the place of that, here it is I by A is equal to 1 by rho into V by L. So V is equal to rho L by A into I. So what is this one, beta? Here it is resistance. V is equal to R into I. Clear? This is how you have obtained that V is equal to IR. Clear? Let us have one question on this one before starting the magnetostatics. I'll going to turn the page. Yes. Observe here. An imperfect conducting rod of circular cross section has radius of 1 meter. The conductivity of the rod varies as sigma is equal to 10 to the power of 5 into rho minus 10 to the power of minus 2 mho per meter is subjected to external axial electric field E is equal to 10 Z cap volt per meter. Find current crossing through the surface Z is equal to 4 meters in Z direction, Z direction. An imperfect conducting rod of circular cross section has a radius of 1 meter. The conductivity of the rod varies as how much beta? Sigma is equal to 10 to the power of 5 rho minus 10 to the power of minus 2 mho per meter is subjected to external axial electric field. E is equal to 10 Z cap volt per meter. Find the current crossing through the surface Z is equal to 4 meters in Z direction. Clear? Observe here, beta. Let me draw the coordinate system here for rough understanding. Here it is the x-axis, here it is the y-axis, here it is the z-axis. Where this external electric field is, let me change the coordinate system. I'll take this as a x, this as a y, this as a z according to my convenience. Nothing wrong. So the external electric field is in which direction? Z direction. That means the electric field is like this. E is equal to 10 Z cap. I'm placing and the cylinder and this electric field is axial. Yes, For that to happen, the cylinder must be somewhere here. Clear? Yes. So where the is asking what is the current crossing through the plane Z is equal to 4 meters. Z is equal to 4 is somewhere here, beta. Okay, fine. So first what I'll do, I'll find out the conduction current. From the Ohm's law, what is this J? J is equal to sigma into E. What is sigma? 10 to the power of 5 into rho minus 10 to the power of minus 2 into 10 into Z cap. J is equal to 10 to the power of 6 into rho minus 10 to the power of minus 2 into Z cap. Units are ampere per meter square. Yes. So once you have got a conduction current, can't you find out the surface conduction current density ampere per meter square you have? Can't you find out the what is the total current crossing the surface? Yes. Let me turn the page here. So how do you find out the surface current beta? I is equal to surface integral of J dot dA beta. But what are the limits here? Here it is a Z is equal to constant plane. So the rho and phi will be varying. So here it is. What are the limits here? Z is equal to 4 meters. And what is this rho beta? Rho is from 0 to 1. Phi is from 0 to 2 pi. Clear? So what happens to the differential length? Here it is rho comma phi comma z. Scaling factors are 1 comma rho comma 1. Here it is rho d rho d phi z cap plus rho d phi dz rho cap plus dz d rho phi cap. So here it is z is equal to 4 meters. Then what happens to the dz? Dz is equal to 0. That means next to two terms are 0. This implies dA is equal to rho d rho d phi z cap. Let me go back. So just to substitute beta here. So what happens to the I? I is equal to surface integral of J. What is the J? 10 to the power of 6 into rho minus 10 to the power of minus 2 z cap. Dot product with rho d phi z cap beta. Clear? So I is equal to 10 to the power of 6 into rho minus 10 to the power of minus 2 into rho d phi 10 to the power of 6 into rho square minus 10 to the power of minus 2 into rho into d phi 10 to the power of 6 into rho cube by 3 minus 10 to the power of minus 2, rho square by 2. The rho limits are from 0 to 1 beta. Here it is 5. Limits are from 0 to 2 pi. Substitute upper limit minus lower limit. Yes. Let me turn the page here. So here it is. I is equal to 10 to the power of 6 into 1 by 3 minus 10 to the power of minus 2 into 1 by 2 into 2 pi. How much is that? Check out this value. 2.06 into 10 to the power of 6 amperes beta check out, or 2.06 mega ampere. Such a heavy current. Okay, fine. Let me turn the page here. Very good. Now let us start the topic number 3 beta, magnetostatics. Okay. Magnetostatics. See here, in the case of electrostatics, we have started with what is called a Coulomb's law. Yes. First, what we have done, we have defined what is called electric force. Later, we have defined what is called electric field. First, we have dealt with the force. Later, we have dealt with the field. But here, we're going to do reverse. First, we'll discuss the field concept here. Why? Because magnetic force expression is a little bit complicated. So we'll take that little bit complicated thing little bit later. First, we'll focus on what is called a magnetic field. And after that, we'll focus on the magnetic force. Clear? Yes. So there in the electrostatics, we had what is called a Coulomb's law. Here we're going to have what is called a Biot-Savart's law. Coulomb's law describes about the electric field. Biot-Savart's law describes about the magnetic field. Yes. So let us start our discussion with what is called a Biot-Savart's law. Let us consider a current carrying conductor beta. Maximum 1 week. Maximum 1 week I'll take to complete this one. Okay. It's a gate plus engineering service course. Fine. Biot-Savart's law. See, whenever there is a current carrying conductor is there, how the current flow happens that we have already seen from the Ohm's law. When the current, when the current carrying conductor is subjected to the external electric field, the electrons are being attracted, current flow takes place, and there will be a current density. So when the current flows, what happens? There will be a a magnetic field around this one, isn't it? So when there is a current carrying conductor is there, there will be a magnetic field around this one. Fine. So what is the nature of the magnetic field? That is given by the Biot-Savart's law. Observe carefully, beta. Here is a what is called a current element. I'll consider. Observe this one carefully. Here is a current element. What is the meaning of that? Here is a current element. The current is flowing in this direction. If the current is going up, what would be the direction of magnetic field? This is given by the right hand thumb rule. You need to put your thumb in the direction of current flow. Your fingers will going to show the direction of magnetic field. Yes. So the direction of magnetic field is like this. Clear? Yes. So that is the direction of magnetic field. So this is the direction of magnetic field. What is the direction of magnetic field, beta? This is the direction of magnetic field. If the current is flowing down, then the magnetic field would have come, it would have like this. Yes. So how much is the current flowing through this one? I amperes of current is flowing through that one. And what is the length of this one? The length of that one is dl beta. And what is the direction of current flow? The direction of current flow is represented with the bar. Yes, this is called a current element. What it is? Current element. Here it is ideal. Here it is current element. Current element describes the current flow in the conductor, length of the conductor, and it is bar. What is the meaning of bar? It is the direction of the current flow. Clear? Yes. Now observe here carefully, beta. Let us consider somewhere here there is an origin. I want to find out the magnetic field somewhere here. The location, the distance from here to here is R1. The distance from here to here is R2. So I want to find out what is the electric field in this plane. If I consider electric field on the, magnetic field in that plane, what is the direction of the magnetic field in that plane? That will be inside. If I consider here, inside. Suppose if I consider here, it will outside. Why? Because the magnetic field is going here, it is inside. Here it is coming outside. In this plane, it is inside. In this plane, it is outside. So what I mean to say here is the magnetic field here, it is inside. I'll call it as a dB. What is the dB? Magnetic field due to the small piece of a current element. Yes, let me frame a vector from here to here. So here it is R12 vector. R12 vector, and what is this one? This is a unit vector. R12 cap. Clear? And the vector notation and everything you know. What is the vector notation? Listen carefully. What is this R12 vector beta? R12 vector is equal to R2 minus R1. What is this unit vector R12 cap? R12 vector by its magnitude. Or you can also write it like this. R12 by its magnitude. Clear? Yes. Okay, fine. Now here the question is, what is this Biot-Savart's law? What is this Biot-Savart's law is saying? The Biot-Savart's law states about the magnitude of the magnetic field beta or direction also. What is this magnitude according to the Biot-Savart's law? The magnitude of the magnetic field is proportional to the current and proportional to the length of the current carrying conductor. If the more current is flowing, there will be a stronger magnetic field. If the less current is flowing, there will be a weaker magnetic field. Yes, and if it is the length of the current carrying conductor is too long, there will be a strong magnetic field and so on. And it is also satisfies what is called an inverse square law. R12 magnitude square beta. So here it is. dB vector is equal to mu by 4 pi I into dl by R12 magnitude square. What is this mu by 4 pi epsilon? It is a proportionality constant. Yes, I'll talk about that one later. Let me turn the page here. So what is this one beta? Mu is equal to mu naught to mu r. This is called permittivity. Permeability, sorry. What is this mu r is called? It is relative permeability. What is mu naught beta? Mu naught is equal to 4 pi into 10 to the power of minus 7 Henry per meter. Here it is absolute permeability. Okay, fine. Let me go back here. This is dB vector beta. dB vector is equal to mu by 4 pi into, I'm writing one more time, IDL divided by R magnitude square. Clear? Yes. I want to write this one in the yes. I want to decide the magnetic field direction here. Direction, it is only the magnitude beta. I want to decide the direction. Yes. So what is the direction here? How do you decide the direction? By taking what is called a cross product. I'll first write down and later I'll explain. These are most of the people are not comfortable. This is where the most of the students are not comfortable because deciding the direction of the magnetic field involves what is called a cross product. Right hand thumb rule. What it is? Right hand thumb rule. Listen carefully, beta. So here it is. dB vector is equal to mu by 4 pi into IDL cross R cap by R12 Just a minute. Here it is. Yes. So here it is. Ideal cross R12 cap divided by R12 magnitude square. There is a cross product here, beta. There is a vector here. Cross product with unit vector. What is this is indicating? What this is indicating? This is indicating the current direction. Cross product with unit vector. So what is the magnetic? Why you are taking the cross product there? Because it's just a right hand thumb rule, not more than that. So the current direction cross unit vector. What it is? Current direction cross unit vector. Let me go back. So this is a current direction. And this is a unit vector. If you take the cross product of these two, what happens? Current direction cross unit vector. If I take the cross product of these two, my screw will go inside. So that is what the direction of the magnetic field is. For example, if I want to find out the magnetic field somewhere here, what you need to do? Here it is current direction cross unit vector. You need to take the cross product of these two. Current direction cross unit vector. If I rotate my screw like this, it will come outside. So here the magnetic field is outside the board. Here in this plane, here it is inside. Clear? Observe here it is current direction. Cross product with unit vector. Clear? Yes. So that is the magnetic field direction. And one more thing here. There is a note here which its units are Weber per meter square beta. There is a note here. There is a relation between B and H beta. B is equal to mu into H. B is magnetic flux density. Units are Weber per meter square. This is magnetic field intensity. It is ampere per meter. So you can write down the H vector from here. What is the H vector? dB is equal to, you can just remove this mu here. You're going to get the H vector. Let me turn the page here, beta. I want to focus more on this magnetic field direction. What it is? Current direction cross product with unit vector. Current direction cross unit vector. So what is the magnetic field direction? Note beta. And before that, what is the H vector beta? dH is equal to 1 by mu pi, 1 by 4 pi. Ideal cross R12 cap divided by R12 magnitude square. Let me go back. So what is the magnetic field? Note. What is the magnetic field direction beta? Magnetic field direction. Magnetic field direction is equal to current direction cross product with unit vector. So the magnetic field direction is equal to current direction cross unit vector. Or simply you can write Magnetic field direction is equal to current direction cross unit vector. What is the unit vector beta? It is the shortest distance vector where unit vector is shortest distance vector from source point to field point. That is, I'll explain this one. Source point to field point is a unit vector. It is a unit vector. Okay, I'll elaborate this note. Before that, we'll go for a break. It is nothing but a right hand thumb rule itself better. Okay, let us have some break for a while. After that, we'll continue with this one. Yes, welcome back, bed. Okay. What is the magnetic field direction? The magnetic field direction is current direction cross unit vector. So the magnetic field direction is current direction cross unit vector. Let me explain this one with the help of one example. I'm going to turn the page here. Now let us consider the current carrying conductor. Here is the current flow. This is the direction of current flow. If this is the direction of current flow, what would be the direction of magnetic field beta? You need to put your thumb in the direction of current flow. Your fingers will show the direction of magnetic field. So here is the thing. So if you consider on this plane, the magnetic field is inside. On this plane here, it is outside. Isn't it? Yes. So let us try to find out the magnetic field at the different instants. Okay. Fine. Observe here beta carefully. Let me write down step by step. I want to find out the magnetic field somewhere here. I want to find out the magnetic field somewhere here. I want to find out the magnetic field somewhere here. How do you find out the magnetic field direction? It is a shortest distance, current direction cross, shortest distance vector from source point to field point. Yes. So here is a current direction. Cross unit vector. It is the shortest distance vector. I want to find out the magnetic field here. So I need to draw a shortest distance vector from here to here. Yes. So what is the shortest distance vector? Like this. Here it is R1 cap. So what is this one? Here it is current direction. Take the cross product of these two things. Current direction cross unit vector. Yes. So here is the magnetic field is inside here. Here it is B1. I want to find out the magnetic field here. There also this is inside. But here current direction cross unit vector. What is unit vector? It is the shortest distance vector from source point to field point. Here is a source point. Here is a field point. Clear beta? So you need to make a vector from here to here. Yes. Here it is field point. Here it is source point. Here it is source point. Here it is field point. So the current direction cross unit vector. Take the cross product of these two. Current direction cross unit vector. Here it is inside. Here it is B2. So the current direction cross unit vector. Here you need to take the unit vector here. I want to find the magnetic field here. So the current direction cross unit vector. Take the cross product like this. Yes. So here it is R3 vector. Current direction cross unit vector. So if I rotate my screw like this, it will come outside. So here it is B3 beta. Here it is field point and here it is source point. Okay. We'll take one question here to appreciate this one. Deciding the direction of magnetic field. Okay. Let us have a question. I'm going to turn the page here. So ultimately what you need to remember? Magnetic field direction is current direction cross unit vector. Yes. Observe here the question. Two infinitely long wires carrying current are as shown in the figure below. Which components of the resulting magnetic field are non-zero at the origin. Diagram is given. Options also given. Options are XYZ components. Option B, XY components. Option C, YZ components. Option D, XZ components. Here is the x-axis. Here is the y-axis. Here is the z-axis. This is a current flow direction. Yes, what is the answer? Very good. Madhuchandra. So there are two current carrying conductor. One conductor is in the XY plane, other conductor is the YZ plane. Is asking which component of the magnetic fields are non-zero at the origin. Or in other words, which component of the magnetic fields are present at the origin. This way also you can put. Directly you can decide by your right hand thumb rule beta. Suppose for this current carrying conductor, if I put my thumb in the direction of current flow, my fingers will show the direction of magnetic field. So how the magnetic field is like this beta. Here it is outside. Here it is inside. Outside means which direction? X direction. Inside means which direction? Negative X direction. So which component of the magnetic field exists at the origin due to that upper conductor is a minus X component. So which component? Here is a thing here is the magnetic field we want to find out. So the which component of the magnetic field exists at the origin due to that one? It is the negative X component. Okay, fine. And what about this one beta? The current is flowing like this. If I put my thumb in the direction of current flow, my fingers will show the direction of magnetic field. Here it is above, here it is below. Above means which direction? Z direction. Below means minus Z direction. So which component is present at the origin due to this conductor is a minus Z. So what is the answer beta? Option D is the answer. Like this, directly with the help of right hand thumb rule, you can decide the answer. Or otherwise, you can make a use of that note what I have given. What is the note? Magnetic field direction is equal to current direction cross unit vector. Clear? Let me turn the page here. I'll going to redraw this one. I'll going to make the help of that note. Here it is x-axis, here it is y-axis, here it is z-axis. So what is the note I have given beta? Here I want to find out the magnetic field, isn't it? At the origin. What is the note I have given? Magnetic field direction is equal to current direction cross unit vector. Here it is x cap, here it is y cap. Here. Yes. So what is the current direction here beta? So I want to find out the magnetic field here due to this one. So current direction cross unit vector. So what is the current direction? The current direction is in the y. Cross unit vector is the shortest distance vector. Shortest distance vector is this one. Here it is minus z cap. So current direction cross unit vector is minus x cap. So which component is present at the origin due to this one? Minus x component. And what about this one, beta? Current direction. What is the current direction? Is x cap cross unit vector. What is the unit vector? Here it is minus y cap. So here it is current direction cross minus y cap is minus z cap. So which components are present at the origin due to this one? Minus x cap, minus z cap. Clear? What is the answer, beta? Option D is the answer. So like this, you need to make a use of, we're going to use throughout our magnetostatics, throughout our subject. Whenever we want to decide the direction of magnetic field, we're going to use this note. What is the magnetic field? Current direction cross unit vector. Okay? Okay, fine. Before going into the numericals, let us have some theory here. What is that theory? Let us have the look over the current, different types of current distributions. Yes, types of current distribution and magnetic field expression. Types of current distributions and magnetic field expression. So when we are discussing the electrostatics, what was the different types of charge distributions we have seen? Point charge, line charge, sheet charge, volume charge, isn't it? But when it comes to the magnetostatics, there is nothing like a point current. There is no meaning for the point current. Point current means charge which is staying there itself. If it is not moving, that is not a current. So the minimum dimension required for the current flow to happen is a line. So the minimum current is a line. Minimum dimension is a line. So here we will be having a line current, sheet current, and then volume current. There is no meaning for the point current, beta. Yes. So let us start with the what is called a line current. Line current. It is represented with the I. Units are ampere. Array. It is not ampere per meter, it's just ampere. Why like that? Let me first explain. After that, I'll justify. So the only reason is why it is called line current. The only reason is current is flowing in a line. How? Observe here, beta. Current is flowing in the line. As the current is flowing in a line, it is called line current. The current flow is I, and the length of this one is DL. This current you already know. It is a very popular current in your circuit theory. as well. I want to find out the magnetic field at a distance of r. What is the magnetic field at a distance of r beta? How do you find out? dB is equal to mu by 4 pi into IDL cross r cap by r magnitude square. This is the magnetic field due to the small piece of current element. If you want to get the overall magnetic field, what you need to do? You need to perform what is called a line integral. Mu by 4 pi IDL cross r cap by r magnitude square. B is equal to mu by 4 pi line integral of IDL cross r cap by r magnitude square. Here it is Weber per meter square. And you are having what is called a current element here. Current element is I into dl beta. Its units are ampere meter. Let me turn the page here beta. Now let us have a second kind of current. What is called a sheet current density or simply sheet current. Number 2. Sheet current. It is represented with the K. Units are ampere per meter. It is ampere per meter. Why like that? I'll justify. Now let us take I is the total current. I is the total current is distributed over the surface beta like this. I is the total current which is distributed over the surface. Now let us consider a line here. What is this one? DL. And it is having some area beta. How much is the area dA? Now I'm going to introduce some new current crossing through unit length. Current is flowing in a sheet but crossing the line. Yes, observe carefully. We're going to define some new current. K is equal to di by dl beta. Units are ampere per meter. Current crossing through unit length. So here it is. di is equal to k dot dl. So I is equal to line integral of k dl. So here it is ampere per meter multiplied with the meter. Here it is ampere. Now let us consider, I want to find out the magnetic field at a distance of r beta. For this, what is required is a current element. What is the current element in the case of line current? It is I into dl. In the case of sheet current, what happens? It will become K into dA. You can cross check with the help of units. Here it is ampere meter. Here it is ampere per meter multiplied with the meter square. Keep this one aside. Come here. I want to find out the magnetic field beta. So how do you find out the magnetic field? You need to take the help of Biot-Savart's law. dB is equal to mu by 4 pi IDL cross r cap by r magnitude square. What is this IDL? Is equal to K into dA beta. So the dB is equal to mu by 4 pi K into dA cross r cap by r magnitude square. What is this one? This is a magnetic field due to this small piece of area. This is a magnetic field due to small piece of area. Yes. So if you want to get the overall magnetic field, what you need to do? You need to perform surface integral. Surface integral of mu by 4 pi K into dA cross r cap by r magnitude square. B is equal to mu by 4 pi surface integral of K into dA cross r cap by r magnitude square. Clear beta? Yes. Now let us have the last current, what is called a volume current. I'm going to turn the page here. Number 3. Volume current density, or simply it is called volume current beta. It is represented with the J. Units are ampere per meter square. Ampere per meter square. Let us take I is the total current. I is the total current distributed in the volume beta. How? Let us consider the volume like this. That is the thing. So the current is distributed over the volume, but it is crossing the surface. Huh? See here how beta? Here is a box. This volume is dV beta. But here it is having a cross section here. How much is the cross section here? The cross section here it is dA. The current crossing through this one is a current density J ampere per meter square. Here it is N cap. Clear? Yes. Now I want to find out. I will define this J. This J already we have defined in our today session itself. While defining what is called a Ohm's law. What is this J beta? J is equal to di by dA. Units are ampere per meter square. So di is equal to J dot dA. If you want to get an overall current, what you need to do? Surface integral of J dot dA. What are the units here? It is ampere per meter square multiplied with the meter square. Here it is ampere. Now I want to find out the magnetic field at a distance of R beta. To find out the magnetic field, what is required is a current element, isn't it? So what happens to the current element? Let me fix here itself. Here I into dl is equal to J into dV. Units are ampere meter. Here it is ampere per meter square into meter cube. Okay. So what is this Biot-Savart's law beta? dB is equal to mu by 4 pi into IDL cross R cap by R magnitude square beta. So in the place of mu by 4 pi, here it is J into dV cross R cap by R magnitude square. So the B is equal to volume integral of mu divided by 4 pi J into dV cross R cap by R magnitude square. So the B is equal to mu by 4 pi volume integral of J into dV cross R cap by R magnitude square. Let us try to justify the limits units here. It may be confusing for some of you. That I'm going to explain with the help of some simple analogy. Yes, see here beta. I'll justify this one. See here. Here, these are the bunch of current carrying conductors. The bunch of current carrying conductors are like a volume. So the current is flowing in the volume, but it is crossing the surface. So it is called volume current. Why? Because the current is flowing in the volume, but it is how it is defined, beta? Current crossing through unit area. Clear? Current crossing through unit area. Current is flowing in the volume. That is the reason why it is called a volume current. But it is defined. How it is defined? It is defined as current crossing through unit area. Unit area. But in the case of electrostatics, the charge was present in the volume and the definition was also volume. But here, current is flowing in a volume but crossing the surface. Dimension is volume, definition is surface. Let me go back here. Number 2. Here it is. Current is flowing in the surface, beta, but crossing the line. It is like this. Here it is like this. Bunch of current carrying conductors. Current is flowing in the surface, beta, but crossing the line. What is the current crossing through? Unit length. Yes, that is number 2. Beta, number 1. Current is flowing in a line, beta, but it is crossing the point. Okay, you must be careful when you are dealing with the units here. Line current is not ampere per meter, it is ampere. Sheet current is ampere per meter. Volume current is, or current density is ampere per meter square. You must understand this difference. Clear, beta? And during this discussion, I have given one very interesting observation. Here it is a current element, I into dl. Here it is I into dl is equal to k into dA. Here it is I into dl is equal to j into dv, beta. Let me turn the page here. So note, there is a current element here. Current element units are ampere meter, beta. So what it is? IDL is equal to K into dA is equal to J into dV, beta. Once cross check these limits, units. Here it is ampere. Here it is meter. Here it is ampere per meter, meter square. Ampere per meter square, meter cube. Okay, beta. Okay. Now, what is important for our exam? You should know all these things, current elements. Later also, we're going to make a use of them. Now, you need to remember, let us have some formulas here. For your exam, you need to remember the magnetic field due to the finite length conductor, infinite length conductor, magnetic field due to the circular loop, magnetic field due to the infinite sheet. So these are the 4 formulas, and in between you will get one more formula. So total 5 formulas you need to remember for your exam. Clear? So let us try to see the first 2 formulas here. Magnetic field due to, what it is, beta? Magnetic field due to finite length current carrying conductor, or simply finite length conductor, which is carrying the current I amperes. magnetic field due to the finite length conductor. Clear? Observe here, beta. Here is a finite length conductor. Here it is a z-axis. I am showing the finite length conductor with the boundaries, beta. Here the current is flowing like this. How much is the current? I amperes. Current is flowing up. So what would be the direction of magnetic field circling around this? Here it is B phi. Okay. Now observe here, beta. I want to find out the magnetic field somewhere here. So here the magnetic field would be inside beta. And the perpendicular distance from here to here is rho. And here what is the angle it is making with respect to the corners? Here it is making angle. This angle is alpha 1. This angle is alpha 2. Okay, beta. Fine. So see here, how do you find out the magnetic field due to this one? You have to use this formula, this expression. B is equal to mu by 4 pi line integral of IDL cross r cap by r magnitude square. Clear? So after for integration and all that story, you will going to get B vector. B is equal to mu I divided by 4 pi rho into sin alpha 1 plus sin alpha 2 E into phi cap. So this is the formula, beta. Current elements means it describes the current element is nothing but it describes the nature of the current carrying conductor. So what is the magnitude of the current? What is the length of the current carrying conductor? In which direction the current is flowing? It is a just description. Is that clear, Yogesh? Gaikwad. Yes. So this is a formula you need to remember, beta. Important. There were 2 marks questions on this formula. In a recent times, 2 years ago, there was a question on this concept. Okay, anyhow, we're going to solve that one in the classroom. Clear? Yes. Okay, now let us try to have, what is this one? Let us try to have, what is this rho is indicating? Is a perpendicular distance. And what is this phi is indicating? It is a magnetic field direction is equal to current direction cross unit vector. Magnetic field direction is equal to current direction cross unit vector. In our example, it is in the phi direction. In general, it may be, how do you find out the magnetic field direction? Current direction cross unit vector. Here it is a distance beta, perpendicular distance. So what is this alpha 1 and alpha 2? Angle made with respect to the corners. Clear? Yes. So if you want to find out, here is the current element. If you want to find out the magnetic field here, what you need to do? You need to see its corners. This is alpha 1 and this one is alpha 2. So observe here, remember this shape. You have to see like this beta. Remember this action. So alpha 1 is like this, alpha 2 is like this. I saw like this. Open. So the alpha 1 is like this, alpha 2 is like this. So from the field point, yes. So how much it is making alpha 1? This one is alpha 2. Suppose if it is an infinite extent line, if you want to find out the magnetic field due to the infinite extent line, what happens? You need to see, if you want to try to see the corner here, it will go up to, so angle will become how much beta? Alpha 1 and alpha 2. I want to modify this one for the yes. Let me turn the page here. I want to modify that formula for infinite line. What happens for the infinite line current beta? Yes. So it is extending up to minus infinite to plus infinite. Here it is Z axis. Current is flowing in this direction. Current is going up, direction magnetic field is around this one. Here it is rho. I want to find out the magnetic field here beta. Here magnetic field is inside. From there I need to see the corners. Yes. So if I see the corners here, I want to see the corners. So what about this angle beta? And what about this angle? I want to see the corners. So that alpha 1 and alpha 2 will become 90 degrees beta. Alpha 1 is equal to alpha 2 is equal to 90 degrees. Bas khatam. So what is this B? Then B is equal to mu into I divided by 4 pi rho into 1 plus 1 into phi cap. So B is equal to mu I by 2 pi rho into phi cap. Here it is perpendicular distance. It is a magnetic field direction. What is the magnetic field direction is equal to current direction cross unit vector. Clear, beta? Yes. So now let us take some varieties of questions on this concept. Let us have one question here. Very interesting question. All questions are interesting only. Okay, fine. Let us solve one question, beta, here. I'm going to turn the page here. An 8 ampere current carrying wire flows along the positive y-axis and also along positive x-axis with the current from y to x-axis. Calculate the h at 3, 4, 0. It is 2 by pi z cap ampere per meter. Option B. 4 by pi z cap ampere per meter. Option C. Minus 2 by pi z cap ampere per meter. Option D. Minus 4 by pi z cap ampere per meter. Okay. Yes. See here, let me explain this question. An 8 amperes current carrying wire flows along positive y-axis and positive x-axis with the current flow from y to x. Calculate the h vector at 3, 4, 0. I'm going to turn the page here, beta. So where is my current carrying conductor, beta? My current carrying conductor is on the positive x-axis, positive y-axis. The wire is along positive x-axis, positive y-axis. So the wire is like this. Here it is x-axis, here it is y-axis. So the wire is placed on the xy axis. What is the current flow direction, beta? Y to X. So how much current it is flowing? Y to X. Here it is 8 amperes. Here it is 8 amperes. What is the question where he is asking? He is asking us to find out H vector at 3, 4, 0. 3, 4, 0. Here it is 3, 4, 0. Here it is 3 beta. Here it is 4 beta. So at that point, you want to find out. So what I'll do, I'll going to divide this one into 2 sections. I'll call it as a section 1. I'll call it as a section 2. So the magnetic field here is due to first section, this section. It is not an infinite line, not even a finite line. It is a semi-infinite line. So whatever it may be. So what is the magnetic field here, beta? Due to this one, first I'll find out. Next, due to this one, I'll add that one. I'll do the vector summation. What you need to see from here, you need to see the corners. Yes, from there you need to see the corners. So can you see this corner? No, it is going up to infinite. So I'll call it as the alpha 1 dash. Here it is alpha 2 dash beta. What is the length from here? It is 3, here it is 4. This will become 5. Okay, let me turn the page here. So what is the H1 beta? H1 is equal to I1 divided by 4 pi rho 1 into sin alpha 1 dash plus sin alpha 2 dash into current direction cross unit vector beta. So just substitute all the values. H1 is equal to how much is the current? 8 amperes divided by 4 pi rho beta. What is rho? Perpendicular distance. What is the perpendicular distance from here to here? 3 meters. Sin alpha 1. What is sin alpha 1? Here it is 90 degrees. So it is 1. Sin alpha 2. What is sin alpha 2? Opposite by hypotenuse. 4 by 5 beta. Current direction cross unit vector. What is the current direction? Current direction is in the negative y direction. Current direction cross unit vector. What is the unit vector? Is the x. So here it is minus y cross x. Two by 3 pi. Yes, so here it is 6 by 5 pi. Then H2 beta. Let me go back. How do you find out the H2? From here, you need to see the corners. So what is the corner here? It is going up to infinite. So how much is this angle beta? Sin alpha 1 double dash. This I'll call it as a sin alpha 2 double dash beta. Yes. So what is this one? Here it is. I2 divided by 4 pi rho 2 into sin alpha 1 double dash plus sin alpha 2 double dash into current direction cross unit vector. Eight by 4 pi rho 2 beta. What is this rho 2? What is the perpendicular distance from here to here? It is 4. It is sin alpha 1 double dash is 1 plus sin alpha 2 double dash is opposite by hypotenuse beta. Means 3 by 5. Current direction. What is the current direction beta? Is in the positive x direction cross unit vector. Is in the y direction. So here it is. H2 is equal to 2 by 4 pi 8 by 5 into z cap. So H2 is equal to 4 by 5 pi into z cap. So what is the overall vector beta? H1 plus H2. 6 by 5 pi z cap plus 4 by 5 pi z cap, which is 2 by pi z cap. Units ampere per meter. Yes. Now let us have one more question, beta. Homework problem. Find H, that means magnitude of H, at the center of square loop of current of ions flowing clockwise in z is equal to 0 plane with side D is side D. Options are given. 2 root 2 I by pi D. Option B, root 2 I by pi D. Option C, 4 root I by pi D. Option D, 2 I by pi D. There is nothing like a easy and something like that. That depends on the question and your practice. Mr. Gopal Menon. Why we are finding the H2 here, right? Manikumar. See here, this is a combination of two sections. One section is here, other section is here. The magnetic field here is due to this conductor, as well as due to this conductor. That is the thing. Is that clear, Manikumar? Manikumar Basani. Distance is 2D here, right? Thank you for suggesting. Because here to here D, here to here D. That's good. But I have considered 2D here, right? Thank you, beta. Thank you, Jakka. Vinita Jakka. Okay, I'll open my discussion. I didn't get your Almas Ali. I didn't get your question. Mr. Attendee, see, I can in the classroom, I'll solve the varieties of models. But you need to solve, you need to practice, you need to improve. I'll give the concepts here and I'll solve some models of questions. You need to solve much more varieties of questions. You need to collect the questions from the previous gate, previous engineering service, EC paper also. That is how you need to improve your problem solving capability. I cannot say that if you study my notes, you will score all the 10% marks. And never, don't believe in such statements. Just by having a classroom notes and solving the classroom numericals, you can get a score. Don't believe in such statements. You are correct, Bimalendu. Almas Ali, I didn't get your question. Can you repeat again? Okay, multiple question, multiple conductors, this one. Yes, there is a possibility. We'll take varieties of questions. Here you can take it as a multiple conductors itself. There is a one conductor here, there is a one more conductor here. We'll take some hexagonal. Here it is a square. Okay, this is a square of side D. Okay, let us open our discussion for the doubts. Vishnu.
Yes, sir.
Yes, better.
Sir, in method of images. So my doubt is there what we did was we consider a grounded plate that we replace it with a charge equivalent opposite in sign and equivalent magnitude.
Yes, you are correct.
Sir, my doubt is, sir, if you keep a plus Q charge over an infinite charge of, infinite sheet, then the induced charge is also minus Q only, no, sir, on the top layer.
Yes, sir.
So since we can't calculate this, if you that is overall charge on the surface, if you add, will you get minus Q?
Yes.
So what we are doing is since bottom is grounded, the positive charges induced in the bottom will be grounded. So only minus Q collectively you are taking it as 1 point, modeling it as
Yes,
one
exactly,
single charge.
exactly.
Okay, sir. So that's how you.
That is what the image star technique is.
Okay, sir. And sir, then next thing is this regarding the sheet current and volume current. So the sheet current is like what you said, like you are taking 3 pens and we are taking a perpendicular cross section area. So we are calculating the current through that. But then in that case, this line current and sheet current are almost same only, no, sir. That is, if this individual conductor is taking, it becomes a line current.
But it is a joining of points will lead to the line. See the
Sir.
figure.
Sir, here the individual thing is a line current only, no? So this individual white
Individual thing is line current, but what I just for our convenience, I have drawn like individual things. But it is a tightly packed one.
Okay, sir.
You cannot treat them as individual ones.
There are infinitely many such compressed together.
Infinitely like that.
And then in that case, in volume, how, sir, that will be extended in 3 dimensions, sir.
Yes.
So in this thing alone, we are taking like all these conductors are along one direction, sir. I mean, all these line currents are along one direction in volume.
Yes,
current.
it is tightly packed current carrying conductors. You can treat. Just for the visualization, I said like that.
Sir, my doubt is again here only, sir. Here, this whatever we are considering this current that is coming out of only one particular area dA. So isn't it same as that of sheet current?
No, sheet current is again something different. No, current is flowing in a volume here like this.
Yes, sir. But again, the cross-section area, we're taking it as sheet. That is the same logic we use in sheet charge also, sir.
But that is not defined like this. It is current named based on dimension you are considering. In which direction it is dimension it is flowing? It is flowing in the volume.
All right, sir. Thank you, sir.
All right. Pasha.
Good evening, sir.
Yes, beta.
Sir, in page number 179.
179.
179.
179. Yes, beta.
Sir, in 120. Yes, in that only. Sir, from main charge plus Q that is going into the second also, no, sir? Means we are going from positive to down is minus Q is coming. One more. It's also going from the 120 degree also, no, sir? From
going from 120 degrees also. That I have not shown. It also it will go minus Q.
Then
with respect to
3, no, sir.
Plus Q. Minus Q. Plus Q. It will not going to start from there also.
Yes, sir, but it's not going into that main, no, sir. It's come.
It will go check out from this one. Minus Q. With respect to this one. Plus Q. With respect to this one. Minus Q. It is going.
Sir, could we take in that consideration it's as a three charges are come. 3 charges. Minus Q plus Q minus Q.
I didn't get your question. Can you repeat again?
Sir, it's a note is there, no, sir. If the image of the image charge exists in the region of the intersect, then the method of image techniques can't.
Little bit louder, brother.
Okay, sir. Sir, is there note if the image of the image charge exists in the region of intersect, then the method of image technique can't be used?
Yes.
Sir, in that case, the plus Q is not intersect in the another region. Means we take as the main charge.
plus Q.
Sir, that main charge is there, no, sir.
Ah,
The image of that it's going to the next surface means that inclined.
ah.
Then it can't be as the image of image charge.
But that is not happening here. This is with respect to this one, the image for this one is this one. With respect to
sir.
this one, the image for this one is this one. Again, with respect to this one, the image for this one is this one. Unfortunately, the image charge or image of the image charge is coming in the region of interest. That should not come. So there you cannot use the method of images.
Okay, sir. Sir, could you draw one perpendicular line to that plus Q in the inclined angle, inclined surface?
This one, this line, huh?
Not sir, inclined angle, inclined.
This one, huh?
But yes, sir.
What happens if this is the case?
In that case, there's also an image charge comes.
Two sheets you want to have, huh?
No, sir, same sheet only. In that sheet.
Why you want to draw like? Why you want to draw a line like this?
That image charge will come in.
So what is this line is indicating? Is that an infinite sheet?
Sir, what? Hello, sir. Sir,
I cannot draw a line wherever I want. I need to draw only line. If it is extension of the semi-infinite sheet, I need to make it as an infinite sheet. That's all it is.
Hi. Yes, sir. The
I cannot draw like this.
Yes, I got, sir. The image charge means the perpendicular distance from the surface, no, sir. That's I'm telling that from the main chart, the perpendicular distance come into the inclined angle also.
Not perpendicular distance, brother. Did I say like that? Just to image for this one is with respect to this one, the simple logic is this one.
Yes, sir.
With respect to this one, see how I am drawing. Is image of this one. With respect to this one, with respect to sheet, the image is this one. That's the thing.
Okay, sir. Means there is only three. Sorry,
not
two.
only three, it will not stop there. It will continue further. With respect to this one, the image of this one is right. With respect to this one, the image for this one is like this. Again, with respect to this one, the image for this one is like this. It will continue infinite lines.
Sir, I have drawn in yesterday class. Sir, in the absolute potential, we are not considering as the K, no, sir. Sir, when we get not consider means it not mention that question, no, sir. Is the absolute potential or not? How can we imagine that as absolute not?
One thing, see, if you are finding the potential at some particular point, you will have a residue. Conceptually speaking.
Okay, sir.
So when you are solving the question for potential at some particular point, first you need to search for residue. If there is any extra information is not given in the question, you have to consider that residue to be 0.
Okay, sir. It means past any value.
Okay.
Yes, sir.
Right, fine.
Thank you, sir.
Mr. Swain.
Hello, sir.
Yes, beta.
Good evening, sir. Sir, I have doubt that in a current carrying loop, we have that current is constant throughout that line. But if we rotate that wire so that in a irregular fashion, then also because that current density is having some direction. Current density.
Yes.
Have some direction, and that will it not violating that current is changing due to orientation of that wire, means wire can be, we can place any type.
See here, on the whole, see, when you are doing with the, see, when you are dealing with the electrical forces, you will neglect the nuclear forces. When you're dealing with the nuclear forces, you neglect something, interatomic forces, something like that. You'll do some approximations here. So we do not talk about that much physics. When the wire is rotated, obviously there will be a change in the electron density.
But the current in practically also constant.
Little bit louder.
But current is actually in the practical also constant.
Not constant, strictly speaking, but you will do some approximations.
Okay, means current is not.
Obviously, it is not constant. If you consider everything into the consideration, we'll study one at a time.
Okay.
That is what we'll do in the physics also, isn't it? When you are dealing with the, if you put it in the order, first is the interatomic forces, nuclear forces, magnetic forces, electric forces, isn't it? I think this is the order. Gravitational forces.
Yes, sir. Yes, sir.
So when you're dealing with one force, you'll neglect other things. That is the thing. And if you mix up all the things,
And
the force will be the tedious thing.
yes.
If you, your question is something much related to the physics.
Okay, no, actually means I think that the current is constant. Then how is it possible if current density is changing? Sir, another
The question is valid, but when you are dealing with one force, we are only stick to that one. We do not consider other things.
Yes, sir. Sir, another doubt is that in the method of image, that this is a conducting plane, infinitely conducting plane. Infinitely conducting plane, and all the flux line are it is absorbing. Or okay, then can we take it as a Gaussian surface?
Gaussian surface.
Because for that, let's suppose that a charge is enclosed in a Gaussian surface, then total flux is passing.
Gaussian surface is an imaginary surface. It is a conducting surface. So the scenario, it is a scenario. Gaussian surface is a technique. It's the technique to find out the electric field. But this method of images is the scenario. It is the case you are having. You are having an infinite sheet and you are having a charge. Then how can you tackle with that? Such a complicated thing can be tackled easily with the method of images.
Okay, and so here also that flux line is same passing like this. That is total flux line is passing that.
Obviously, it is an infinite sheet. There is a charge here.
Yes.
Now here you can apply Gaussian surface if you want.
That Gaussian surface is a uniform, means that surface is where potential is constant.
Over this surface, huh? Why?
Means sir, that potential electric field is constant. We are having in that Gaussian surface.
Here you can say electric field constant. Here you can say electric field constant. These are the equipotential surfaces. Okay. Right. Avinash.
Good evening, sir.
Good evening, beta.
Sir, slide number 177.
Slide number?
177.
Let me increase the voice, beta. It's too. Can you speak out?
Sir, slide number 177.
177. Okay, beta.
Yes, sir.
177. Yes. Yes. What's your doubt?
Sir, here we have taken that force towards the plate, sir. Then why we consider towards plate?
Question. Read the question.
Yes, sir.
Force is asking the force nature also. Which charge you have placed? You have placed the positive charge. So it will going to induce the negative charge on the sheet. That means force will be from positive to negative. That is the electric.
All right, sir. Sir, 204. Slide number 204.
204.
Sir, a previous slide, sir, graph I have not understand, sir, how the graph.
This
came
one,
out. Yes, sir. Yes, sir.
read the question carefully. So there is a XY plane beta.
Yes, sir.
This is the x-axis, this is the y-axis. So where is this current carrying conductor is placed? This current carrying conductor is placed in the positive x-axis and positive y-axis. You are having a wire. So you are bringing that wire and you are placing on the positive x-axis, positive y-axis. With the current flow from which direction? Y to x direction. That is also mentioned in the question.
Okay.
Got the question? Okay. Yes. Any more questions? Okay then. Bye. Any more questions? Okay, then I'll going to close the session. Try that question. Avinash.
Sir, the alpha 1 and alpha 2, you have considered what is the name of that angles?
Angle made with respect to corners, you can say. How much they are making angles with
What's
respect to the corners?
it?
Corner of the current carrying conductor. Here you want to find the magnetic field and you are looking the corner. So how much angle it is making? It is alpha 1, this one is alpha 2.
Okay, sir. Sir, these two angles are always same or maybe different, sir?
No, they may be different. How can you can expect to be same? See, here it is different. Here it is same. Here it is different. That depends on at what location you are finding the magnetic field. For example, you want to find out the magnetic field here. So this angle is different, right? This angle is different. Here it is alpha 1, here it is alpha 2. Are they same?
Yes.
Or I want to find out the magnetic field here. So I need to see the corners here. Here it is alpha 1, here it is alpha 2.
Okay, sir. Thank you, sir.
Right, any more questions? Madhuchandra.
Hello, sir.
Beta.
Sir, is that mirror image formula you have shown 360 degree divided by theta minus 1? Is that only valid for theta less than or equal to 90 degree and 180 degree?
No, it is valid only when
Theta
the
is less than
image of the
90
image charge
degrees.
is not in the region of interest.
Then that is only possible when it's less than 90 degree, right, sir?
You can check once, cross check. When you use that formula, you need to cross check with the help of that formula. Once you have to cross check and you have to use that formula.
Okay. Thank you, sir.
Okay, beta. Any more questions? Okay, then I'll going to close the session. Bye, friends. Good night. Take care. Thank you. Good night.